Hello everyone. Today we'll be discussing about microplastics in agriculture soil and how they can impact soil microbiome. To begin, microplastics are defined as plastic particles smaller than 5 millimeters. They can be found in everyday products like cosmetics, clothing, bags, and also plastic bottles. Next, soil microbiome. It refers to the community of microorganisms in the soil, which includes bacteria, fungi, archaea, and protists. These tiny organisms play a vital role in maintaining soil health and supporting plant growth. The issue we'll be focusing on is how microplastics alter the structure and function of the soil microbiome, which in turn affects agriculture and food security. So how does these microplastics get into the soil? They come from many sources, such as the use of plastic mulching films, irrigation with contaminated water, and also the application of plastic-coated fertilizers. Wastewater, compost, manure, and sewage sludge also carry microplastics from cosmetics and cleaning products. In fact, studies show that in China, plastic films are found in about 10% of agricultural land. That's the overview. The rest of the video will explore how microplastics affect the soil microbiome, the consequences on agriculture, and also the potential solution of this problem.
Now let's see the role of soil bacteria in agriculture. Promoting nutrient cycling and crop absorption is one of the most basic and important functions of soil microorganisms. In my country, many people jokingly call them fertilizer factories or nutrient transporters like that. Whatever the joking call them, it has shows that what they have worked. First, let's talk about the nitrogen cycle, because the nitrogen cycle is the most common one, which include the nitrogen fixation, nitrification, and denitrification. Nitrogen fixation, such as rhizobia and legumes, because plants cannot directly use nitrogen gas, and soil microorganisms can convert nitrogen gas into ammonia, that plant can absorb it. And nitrification converts ammonium nitrogen into nitrate nitrogen, and denitrifying bacteria reduce nitrate nitrogen to the nitro gas. You can see the cross-binding ion changes here, and I also put a picture shows the nitrogen cycle. These processes working together to maintain the nitrogen balance in the soil. Soil microorganisms participate in the material cycle, not only the nitrogen, but also phosphorus, organic matter, and so on, which can all participate in improving soil structure and health. The polysaccharide, humus, and other sticky substance secreted by soil microorganisms will act like glue and make soil particles stick together. This can improve the aeration, water permeability, and water retention for the soil. Let's see, for example, after a heavy rain in Malaysia, such soil will not be easily lost. This also makes the root growth environment excellent. The good soil structure provides a suitable environment for the growth of crop roots, promotes root extension and nutrient absorption. In that case, the root will grow deep and make all the things a virtuous cycle. At the same time, the composition, diversity, and activity of soil microbiome communicates can be used as important biological indicator to assess soil health. Soil microorganisms can help crops resist the adverse effects and pests. They can actually be called natural bodyguards and doctors. They can promote plant growth. Some soil microorganisms can secrete plant hormones, stimulate plant growth or development, and increase crop yields. At the same time, they can enhance crop resistance. They may rob pathogenic microorganisms from nutrients and space through competition or antagonism, produce some antibiotics or other things that might make other bacteria be inhibited or die. Also, soil microorganisms can improve plant resistance to drought, heavy metal pollution, and other abiotic adverse effects by improving water using efficiency.
Now we look at how microplastics affect the soil microbiome. Basically, they are swimming with physical, chemical, and biological effects. So let's break them down one by one. First, microplastics can cause physical issues in soil. They block soil pores, which stop air and water from moving freely. They also damage soil structure, making it weaker. Because of this, soil can't hold water well, and gas exchange become harder. Finally, microorganisms lose the space to live because their habitat is compressed. Looking at the chemical side, microplastics release toxic chemicals like BPA and phthalate, which are harmful to microbes. They also erode or carry heavy metals and pesticides, which pollute the soil. These substances can cause oxidative stress, which damage microbial cells. On top of that, microplastics may change soil pH and redox conditions, making the soil less healthy. And when we look at biology, microplastics slow down enzyme activity in microbes, so they don't function as well. They also change the mix of microbial species in the soil. This messes up nutrient cycles like carbon, nitrogen, and phosphorus, and the teamwork between microbes and plants gets weaker too.
Hello, I am Ahlam Said Hamid. I'll be talking about the microplastics, consequences of microplastics to soil, microbiome, and food security. When microplastics enter the soil, they destroy the balance and the community of microorganisms that break down organic matter and cycle the essential nutrients to plants. Microorganisms like bacteria and fungi that are usually responsible to help convert nitrogen or phosphorus to plants become less active or die off, and as a result, the soil loses its natural fertility, making it less capable to support healthy crops without the heavy use of chemical fertilizers, which are also bad for the soil microbiome. Another thing microplastics do and cause is poor plant growth and low crop yields. The healthy soil microorganisms form relationships with plant roots, helping with nutrient uptake, disease resistance, and root development. When microplastics interfere, they usually weaken these relationships, leading to stunted roots and growth, poor nutrient absorption, lower productivity, and can also make the plants more susceptible to diseases and pests. Soil microbiome is also responsible for maintaining the soil structure. They store carbon, they help the land recover from stress after overuse. Microplastics degrade the microbial community, so the soil loses its resilience and becomes more prone to erosion, compaction, and the loss of fertility. This degradation accumulates over time, threatening the long-term sustainability of agricultural systems and making food production very much less reliable, especially in the vulnerable regions. Disruption of the soil microbiome can also lead to an accumulation of toxic substances in the soil. Recent studies have shown that land accumulates and contains up to 23 times more microplastics than the ocean, which is very unfortunate. These plastics release chemicals such as phthalates or BPA that are absorbed by crops and enter the food chain. Ingesting the food that is grown in such contaminated soils may expose humans to harmful diseases like inflammation, hormone disruption, metabolic disorders, and potentially even cancer.
First, let's talk about possible solutions through biological and technological innovation. One effective method is material substitution, using biodegradable agricultural plastic to reduce microplastic generation at the source. Another promising approach is microbial remediation. Certain microorganisms, such as bacteria and fungi, can actually use plastic as a carbon source, enabling slow but steady degradation. Lastly, we must address sewage and organic fertilizer control. These inputs often contain hidden but significant amounts of microplastics, so managing them at a source is essential for protecting soil health. Now, moving on to the soil health management strategies. Reducing tillage is crucial as it lowers the risk of microplastics migrating to deeper soil layers. Additionally, supplementing organic matter enhances the resistance and the recovery of soil microbial systems. Finally, crop rotation plays an important role in maintaining both microbial stability and biodiversity. Together, these practices help create a more sustainable and microplastic resistant agricultural environment.
To end this presentation, in order to protect and maintain healthy soil, we need to minimize microplastic pollution. Throughout this presentation, we've seen that soil is a vital asset for humans. It's the foundation for essential things in our daily lives like food production and plant growth. Most importantly, we've learned that protecting the soil microbiomes mean protecting agriculture itself. By reducing microplastic pollution, we're safeguarding the future of farming and food production. Shielding soil microbes isn't just important for today, it's crucial for building sustainable food systems and ensuring a secure future for everyone. Thank you.